So basically what we're doing today is I want to show you some real life general applications of where these logarithms could come into play. And basically the answer to that is anytime you have a general equation where inside that general equation you have exponents. And not just exponents, but you have a variable in an exponent. You know, if you look at physics, you look at chemistry, you look at, biology or any class that you take, you run into these formulas, right? And the first few times you deal with this, like this is a formula that you've actually done back probably in Algebra 1. But the types of questions they gave you were very simple. And what I mean is this is the formula for compound interest. We've already kind of talked about this a little bit. And I used this formula to show you what E was, right? But this is the formula for compound interest, where A is the total amount of money. P is your principal, like how much money you put in the bank. R is obviously your rate. N is the number of times it's compounded. And T is obviously time, right? And the first few times you use this formula, you get questions like this. I've got $10,000 in the bank. So where does that go in the formula? If I put $10,000 in the bank, that's my P, right? And my bank gives me 5% interest, right? So that means my rate is 0.05. And then they'll also say it's compounded, let's do monthly, which means what is my number of times compounded here? How often is it going to be compounded? It's going to be compounded 12 times, right? And the first few times you got this formula, the question was like, if I leave this in the bank for 10 years, how much money will I have? So an equation like this, do I need logarithms or anything special to solve this? No, this was basically an order of operations question. It was just, all right, I got to figure out what this mess is here, and I can do that, right? Come on, if I turn my calculator on, I can just go 0.05, divide that by 12, add 1, raise that to the, 120th power, 12 times 10, and then times that number by $10,000. And if that's the case, I'd have $16,000, and they gave me $6,470 basically, right? That's a fairly simple question. But this question gets a whole lot harder. Or this formula gets a whole lot harder if you change the question. The question becomes, using the same formula, I've got a bank that gives me 5% interest, and it's compounded monthly. I've got $10,000, right? The car that I want to buy is $18,000, or let's just do $20,000. How much time do I have to wait? How long will it be before I have my money doubled? Why does this become a harder question to solve? Same formula, but what's the key difference here? Where's that unknown? The unknown ends up in your exponent. anytime you deal with a general formula like this, where you have the potential of your final unknown, the thing you have to solve for, if that's in your exponent, logarithms are going to come into play. With this one, the first one, my unknown wasn't in the exponent. It was just my a. I had to solve for a. I knew everything, so this became a fairly simple question. Now this one is a little bit harder. How would I solve this? What's the first thing I could do with this 10,000? Remember, I want to get t by itself here. What could I do with this? Divide. What's 20,000 divided by 10,000? 2 equals, well, I can figure out this mess. That mess, if I just grab my calculator again, 0.05, divide that by 12, add 1. So I'm here. I got 1.004 whatever raised to the 12t power. What's the next step? Once I get this solved a little bit, I call it get rid of the fluff. 10,000, that's fluff. Get rid of that. This mess, I can simplify that down to here. Once I get it to this point, where I have a number raised to my exponent equals another number. Here's where my goal has to be. What's next? Switch forms. What would this be in log notation? Log base, the 1.004 number of 2 is equal to 12t. All I have to now do is solve this log and then divide by 12. So I would have basically log of 2, make sure I close that parenthesis, divide that by log of my 1.004 number, get that answer, and then divide by 12. And my answer would be, I would have to wait 13.89 years. Does that make sense? These formulas pop up in a lot of different areas. And don't worry, I'm not going to make you memorize all these formulas. This formula, this A equals P times the quantity of 1 plus R over N to the NT, that's your formula for compound interest. If you're talking any kind of money in the bank, things like that, that's your formula. If you look over at page 360, you will see a formula inside an example that looks like B equals 1,000 times 2 to the T over 48, right? This is one example of a bacterial growth formula where, now, do all bacteria grow the same rate? No. So that 48 for the next problem might be a 56 or a 32 because they don't actually multiply out as fast as, some bacteria grow faster. You don't always start with 1,000 bacteria. Sometimes you start with 10,000 bacteria. But in this question would be very easy if they gave me time. If they said, how many bacteria would I have after, a year? But if they say, how long will it be before this 1,000 bacterium turn into 1,500 bacteria, this becomes a little bit harder of a formula to solve because my unknown is still up here. When you do these, step 1, you're going to have to figure out what formula to use. That one's pretty easy. Step 2, plug the given information into said formula. Once you get to this point, what's the very, very next thing I have to do? I have to get it to the point where it's a number raised to the exponent equals another number. I got to get rid of the fluff. In this case, the 1,000 is the only fluff I have to get rid of. So we divide. What's 1,500 divided by 1,000? Just move the decimal over, right? 1.5 what is the next step once you get it to that point? Once you get it to a number to an exponent equals another number, now we can switch forms. This would be log base 2 of the 1.5 is equal to t over 48. I can calculate that log as log of 1.5, divide that by log of 2, right? What's the only thing I got to do left? How do I get rid of that 48? Times that by 48. My answer would be 28 years or 28 weeks, whatever the heck the problem is. Does that make sense? If you look on page 361, there's a formula up at the top. This one confuses people a little bit more. It says A equals A sub 0 times 2, what is it, to the negative t over k? Something like that. Yep. Now, this is the formula for isotope decay, fossils. You want an age of fossil, okay? And this is the formula that you would end up doing. You want to find out how old a rock is. This is the formula you're going to end up using. And basically, the problems that you're going to get are going to say something like, I found a fossil that had 100 milligrams of something, right? And then originally it contained 100. Now it only contains 75, right? So the original, just remember when you solve this, the original number always has to be the bigger of the two numbers. Why is the original going to be the bigger of the two numbers when you are plugging numbers into this formula? What's happening to everything? What's happening to these isotopes? They're decaying, they're going away, right? So just remember the original is always going to end up being the bigger number. Okay? And now in that problem, they give you the half-life. Well, now the half-life in this case is 5,570 years, right? Great. Step one, they give you a problem. You got to figure out the formula. We plug the given information in. What's step two? Get rid of the fluff. What's the only fluff I got to get rid of? Here's the mistake a lot of people make. They do this. Am I allowed to do that? Your Aunt Sally rolls over in a grave when you do that. You can't multiply before you do exponents, right? So please don't make that mistake. What's the way I have to get rid of that 100? Divide. So 75 divided by 100 would be 0.75 equals 2 to the negative t over 5570. Now what do? Switch forms. So I'd switch forms. This would be log base 2, 0.75 equals the negative t over 5570. That I can calculate by doing log of 0.75 divide by log of 2. Get that answer. The last step would just be to do what? Multiply by a negative 5,570. Now, if you ever do a question like this, your final answer comes out to be a negative number. Can you have negative time? What do you think you probably did wrong? If you get a negative answer, what you probably did was you switched these two numbers. If something decays and it starts out small and gets bigger, well, that would have to go back in time for that to happen. So yeah, it makes sense you get a negative number. Check your original when you plug things in. Make sense? Now, here's one that actually is pretty relevant to today's world. If you look at example 3, you have a formula that looks like this. What do you think this formula is used for? This formula is used to calculate how fast like a virus would spread. Like, this is epidemiology in a nutshell. This is an example of, a virus spreading through a population type of thing. What do you think that 15,000 is? How many people you got in town? Now, the 0.8 and the 7499 could vary because not all viruses are as contagious as one another, so some are going to spread more rapidly than others. But this is an example of basically how you can calculate how much time it would take for so many people to have the virus. And you could calculate fairly simple with a formula like this and use it to make major decisions and say, all right, when am I going to shut back down, right? When am I going to make those kind of decisions and say, all right, well, I got a town of 15,000. What do you think the number is that I should take evasive action? Well, maybe I want to know how long is it going to take for 1,000 people to have that virus, right? So I started with 15,000. I want to know how much time it's going to take before I get to 1,000. How would I solve this thing? That looks like a much more complicated formula, doesn't it? Treat it like a butterfly problem. Here's how I would do this. I would multiply without actually multiplying. What I mean is, I have to do 1,000 times that mess, right? Great. I got to do 1,000 times that mess. Equals 15,000. Now, could I distribute here? I could if I want to. What's another way to get rid of a times 1,000? Just divide it over there. Great. 15,000 divided by 1,000. Would be 15, right? What's the next step? Minus the 1, so I get to 7499 e to the 0.8t is equal to 14. Can I switch forms yet? No, I got to get it to the point where it's the number e to the 0.8t is equal to some number. So how do I do that? You divide. So now I'd grab a calculator and just divide 14 divided by that 7499, and I get to here. Okay? Now what? Once you get it to that point, what's the next step? Switch forms. This would be log base e. What's another way to write log base e? Isn't that just natural log? Of what? The 0.001 number, that thing, is equal to 0.8t. So all I have to calculate is the natural log of that mess, got that answer, and divide by 0.8. I'm not sure why it ended up being negative. Oh, did I lose the negative? That was negative. So should have divided by negative, so positive 7. So it'd be 7.8 years in this case, or weeks, or whatever the formula is in terms of. So this is a problem that there's a lot more fluff. Once you get to this point, there's a lot of fluff in there. It's just about simplifying it. Butterfly, not a hard thing to do. But don't actually distribute. Make your life easier. Just divide by the 1,000. -1, divide. Get it to, you just got to get it to here. This is the only goal. Like, you're not thinking logarithms at all until you get to here. Once you get to there, once you get to that point where you have a number raised to an exponent equals another number, that's where you bring logs into play. Does that make sense? Your next quiz, your next test, there are going to be problems like this. I'm not going to make you memorize the formulas. But what I will say, everybody look at page, take a deep breath. I want everybody to take a deep breath. Open your book to page 362, 363. I know it's very scary looking. There's a lot of words on those pages. It's going to be okay. You will survive this. So you're going to have some story problems on the next quiz, next test. Step 1, when you read a question like number 1 or number 2 or number 20, doesn't matter. What is the first thing you have to figure out? What formula to use? It's going to be one of these. And I would go back into the examples throughout the assignment. It's going to be this one. If you see compound interest, if it's talking money, there's your formula. If it's bacterial growth, there's your formula. Don't be surprised if, like in number 1, it's not exactly the same thing, is it? They changed the numbers, but it's basically the same thing. The idea is it's a slightly different bacteria. It grows a little bit different rate, starting with more, so don't be surprised. If they're talking isotope decay, there's your formula. Be able to use it. If they're talking virus spreading through a population, it'll look something like this. But it doesn't have to be 15,000. They could change that in the problem. It doesn't have to be 74.99. It could be a slightly different one. Like if you look at the bottom corner of page 363, there's another example of just a different virus, right? Different town, different virus. It's just slightly different math, right? The basic process is going to be the same. When you read one of these, step 1, figure out what formula to use. I would write it down immediately. Step 2, plug in the given information into the formulas. Step 3, get rid of the fluff. You got to go from here to here, where now you're just dealing with a number to an exponent equals another number. After that, switch forms, and you should be able to solve it. Does that make sense? On the next quiz, on the next test, on the board, what I'm going to do is I'm going to write A equals P1 plus R over N to the NT power. I'm going to write B equals 1,000 to T over 48. I'm going to write A equals A sub 0, right? I'm going to write the formulas on the board. Am I going to tell you which formula to use for which question? No. Am I going to tell you what all the letters stand for and you should be able to? No. I guarantee if you do this homework assignment today, you'll know exactly which formula to use for exactly which questions. That's never the issue. I'm not going to make you memorize the formulas. That's not the goal here. The goal here is, can you, given a formula like this, plug numbers in? Sometimes, a lot of times, the unknown is going to end up being the T. Does it have to be? No. Sometimes they're going to give you the time. and you're going to, all you got to do is solve it. It becomes really easy. Don't think you have to use logs for every single question. That's not going to happen. I will tell you in your homework, which is page 363, you're doing 2 to 20 evens. You're going to, a lot of them, I'd say probably out of the 10 questions, 8 of them, you'll probably have to use logs to solve. But don't be surprised, especially if the first couple, you don't need to use a log because maybe they give you this formula and they just say how many bacteria am I going to have after a year or 2 years. Well, then you'll know the time. Then you just solve it. Okay?